Well, we're going to talk about identities for a few lectures. The difference between an identity and a conditional equation is that an identity is a claim that two sides of the equation, the left-hand side and the right-hand side, are identically equal. That means not depending on the particular value of the variable x, but it works for every value of x that makes sense to plug in to the left-hand side and the right-hand side. Sometimes you'll see identities in algebra. When you try to solve an identity like you would solve an equation, what happens is everything goes away. You end up with 0 equals 0 or 1 equals 1, something that doesn't specify a particular condition on x for it to be satisfied. That's a bad thing if you really want to get your hands on a particular x that works, but it's a good thing if you are observing that two sides of the equation represent the same values. So, lots of facts about trig have been cast as identities so far. For instance, we talked about the quotient identities. That captures the fact that tangent and cotangent can be written as fractions involving the other trig functions sine and cosine. Also, we had the reciprocal identities. The reciprocal identities let you say what cosecant was as reciprocal of sine, secant as the reciprocal of cosine, and cotangent as the reciprocal of tangent. So the fact that these hold independent of the value of the angle, as long as it makes sense to plug in an angle on the left-hand side and the right-hand side of one of these equations and get a value out, the value that you get left and right will be the same. What are some other ones that we've looked at in the course so far? There were the Pythagorean identities. We started with the mother of all, sine squared theta plus cosine squared theta equals 1, and then derived from that a related identity that connects tangent with secant, and another one that connects cotangent with cosecant. Anytime you've got one of these expressions, sine squared theta plus cosine squared theta, if you can identify that in an equation, as part of an equation, you can replace it with the value 1. Since sine squared theta plus cosine squared theta is always 1, that's a useful simplification to have sometimes. Some other identities that we have noted are based on facts about the symmetry of the trig functions. The even-odd identities say that sine is an odd function. That says sine of the angle and sine of minus the angle are the same in size but opposite in signs. One's positive and one's negative. It says that cosine is an even function. Cosine, it doesn't matter if you go to the left or to the right, it's the same value. And tangent is also an odd function. So from those three identities, we've got three reciprocal identities. Reciprocal of sine is cosecant. Reciprocal of cosine is secant. Reciprocal of tangent is cotangent. So those three are the fact about symmetry of one of those trig functions gives information about symmetry of the reciprocal function. What do you do to solve an equation? You're looking for a particular value of the angle that works. What do you do to do an analogous thing for an identity? The word would be to establish the identity, and the way you do that is you show that the identities that you have as raw material, those named identities that were on the slides before this, can be exploited, can be used to reduce one side of the given equation to match the other side. Let's try to do that for one. Let's try an easy one first. How about sine theta times cosecant theta minus cosine squared theta is sine squared of theta. the claim is that this is an identity, that the left-hand side and the right-hand side of this equation always match. A way to see that that happens would be to look at this complicated left-hand side and see if you can reduce it to the right-hand side. One thing to observe is that the reciprocal identities let you replace sine theta times cosecant theta by sine theta times 1 over sine theta. Reciprocal of cosecant is sine. Now algebraically this factor of sine cancels, and that makes this equation match 1 minus cosine squared theta. Now remember the Pythagorean identity, sine squared theta plus cosine squared theta equals 1, and 1 minus cosine squared theta then is sine squared theta. We started with the left-hand side of this equation and worked down through so that we had an expression that matched what was given as the original right-hand side of the equation. What that is establishing the identity. Let's try another one. Cosine theta plus 1 over cosine theta minus 1 equals 1 plus secant theta over 1 minus secant theta. Well, to establish that, we're going to have to try to make the two sides match. I like working with sines and cosines more than the other functions, so let's first of all put the right-hand side of this in terms of sines and cosines. The reciprocal identities say that 1 plus secant theta is 1 plus the reciprocal of cosine theta, so that's what's on top, and 1 minus secant theta gets the same treatment on the bottom. Well, this is worse in a way. It's an uglier fraction than what we started with, but it does have cosines in it instead of secants. So let's keep the cosines and make the form of it a little bit nicer by clearing out this compound fraction. I'll multiply top and bottom by a common denominator. That would be cosine theta, and that will make then, when I multiply this through, cosine theta times 1, cosine theta times this reciprocal makes that factor cancel. So cosine theta times 1, cosine theta times 1 over cosine theta is this value 1, and on the bottom, cosine theta times 1, cosine theta times minus 1 over cosine theta, so cosine theta plus 1 over cosine theta minus 1, and sure enough, that is the other side of the identity as it was given to establish. So we've made one side match the original other side by applying these more basic identities, these trig facts that we've been building, and that will take care of it. One more. Let's try a complicated one. It looks complicated anyway. 1 plus sine theta over 1 minus sine theta minus 1 minus sine theta over 1 plus sine theta equals 4 tangent theta secant theta. Well, this has fractions to work with. It often simplifies a problem involving fractions if you combine them with a common denominator. Common denominator for 1 minus sine theta and 1 plus sine theta would be the product of those two things. So I'm going to multiply the left-hand side through by 1 plus sine theta over 1 plus sine theta for the first term, and 1 minus sine theta over 1 minus sine theta for the second term. That'll make both terms in that combination of fractions have a denominator of 1 minus sine theta times 1 plus sine theta. So multiplying this stuff out, 1 plus sine theta times 1 plus sine theta, just square that binomial, 1 plus 2 sine theta plus sine squared theta. On the bottom, 1 minus sine theta times 1 plus sine theta is a factored difference of squares, so those multiply together to give 1 minus sine squared theta. Same thing on the bottom of the second term, and on top it is, I'm subtracting away 1 minus sine theta squared, and that's what the numerator is here, 1 minus 2 sine theta plus sine squared theta. Well, we were aiming for 4 tangent theta secant theta. I don't know if you see it yet, but it's getting close. One thing to observe is this bottom where the denominator is now 1 minus sine squared in each term could be 1 minus sine squared, or the Pythagorean identity could write it as cosine squared. 1 plus 2 sine theta plus sine squared theta. There's the first term. This minus out front means that when I'm combining this and putting this in the numerator, I change the sign of each term in here. Minus 1 minus a minus 2 sine theta and minus sine squared theta when I combine like terms. So now combining the like terms, the 1 cancels, the sine squared theta cancels, 2 sine theta plus 2 sine theta is 4 sine theta. I've got cosine squared on the bottom. Remember, the original identity to establish had tangent theta and secant theta on the right-hand side. Tangent theta is sine theta over cosine theta, and secant is 1 over cosine theta. So I'm going to write my cosine squared in the denominator split up so that I can account for the tangent factor and the secant factor in that original identity. And with that, it matches what was given as the original right-hand side of this identity. So we've established another one, same strategy in the large anyway, in that we're just trying to apply basic facts about trig functions to simplify one side of the identity to make it match the other side. Now we can make up some general rules that help in figuring out what a good strategy is. One thing is kind of a common sense thing, that it makes more sense to start with something complicated and make it simple than to start with something simple and make it complicated. Usually when you're making things simple, there's a clear trajectory, there's a clear path to follow to get to an end. When you're making things more complicated, there's so many choices that you have that you're hard-pressed to find the right one at random. So, go from complicated to simple. Go from fractions to combined fractions. Write the fraction with a common denominator. Often that will give you something that cancels or a clear next identity to apply. Sines and cosines are very useful for a standard for simplifying. If you can write one side of the identity in terms of sines and cosines, sometimes just doing that is enough to spot a simplification to make, a cancellation that will let you see what the next step should be in the simplification. And the last is a good general strategy for life, that you should always keep your goal in mind. Look at the identity as it was given, the left-hand side, the right-hand side. If you've identified that you're going to simplify the complicated left-hand side, remember what the right-hand side looks like so you know where you're aiming. So here is an inspirational picture to help you remember to keep your goal in mind. That's how you solve identities.